Okay, Giant team members. This video lecture, this statistics video lecture, is on a very important topic. I think I mentioned it in a previous video. I think the two most important topics are one, the measure of central tendency, which is usually a mean or median, which we did in our last video, and then the use of standard deviation. And if you could understand those two concepts, I think you could really begin to not only understand but appreciate statistics and what you're able to understand and discern from the data that you have. So in this video lecture, we're going to talk about standard deviations. And there's two calculations for standard deviation. One is for a population, and the other one is for a sample. And we had the video lecture already on what is the difference between a population and a standard, a population and a sample. And most of the time, we're going to be pulling a sample from something. If you're doing customer satisfaction surveys, you're not going to be able to get every single possible customer that comes in the Giant or could potentially come in the Giant. So you're going to pull a sample, and you're going to try to pull a representative sample of the population of people who come to Giant. And from that sample, we could get pretty accurate information about whatever it is that we're trying to figure out, whether it's customer satisfaction or preferences or whatever. So what we'll do today, don't get freaked out about these calculations. They're actually rather quite easy. I just want you to become familiar with the notation that we're using when we say a sample standard deviation or a population standard deviation or a sample standard deviation. So I don't know why that's open. So let's start here with our normal distribution curve, because I really want to make sure that we understand what a normal distribution curve, and then we'll introduce again that concept of variation or variability into the measurement. So you can see there's three distinct curves here. There's a gold, a red, and a blue curve, and they're all normally distributed, right? They're symmetrical. They have this bell-shaped curve, but some of them are a little steeper, let's call it, than other ones. Now, all three of these curves have a mean or an average of 1,000, and we just happen to be looking at SAT scores here, but we could be talking about anything. Customers served in a day, the waiting time of customers in minutes. This could be anything that we're looking at. So these three bell curves all have a mean or average of 1,000. But notice how spread out they are, going from the blue to the red to the gold. The gold is far more spread out than the blue curve. This is an indication of more variability within this process or within this test, for example, or whatever else it might be. So let's put it in terms of minutes waiting in line. That might be a little easier to understand. This blue curve is pretty tight. So we're going to find that most people wait between 800 and 1,200 minutes, which might seem like a long time, but again, that wasn't the intention of this to begin with. We're saying, okay, that's a long time to wait, but it's still pretty tight, and we're going to find that most, if not all of our observations fall between this 800 and this 1,200 minutes, versus over here where most of our observations are falling between 400 and 1,600 minutes. That's a far greater range of values and a much more spread. So it's much easier to manage this because we're tighter and there's less variability than it is to manage this, which is more spread out and inherently has far more variability. So the way we measure that is with something called a standard deviation. So what I'm going to do is I'll look through, we'll look at both of these equations, and I just want you to become familiar with what each of these symbols means. I'm not going to make you do any longhand calculations. I won't make you do that. You'll see we'll be doing them all within within Excel. But I think it's important that you understand at least what these formulas mean. So I'm going to go ahead and drag over my circle here so we could look at some things. This is the standard deviation symbol, okay? And it's specifically standard deviation for a population. If we move to a sample standard deviation, it's a small or lowercase s. So immediately when you look at a formula or you look at something, if you see this symbol, we're talking about a population. If you see the lowercase s, we're talking about a sample. Okay, so that, again, it's important to distinguish that because as you could see, the formulas are a little different. So both of the formulas have this guy in it, and that's the Greek letter sigma. And all that means is we're going to be adding whatever number of these things that we get. Okay, so just this sigma means sum or summation. You'll often see it in here too in Excel under the calculations. There's a sum, and again, all it's saying is we're going to take whatever these things are in parentheses, and if we have 2, 3, 4, 5, 6, whatever of those, we're going to keep adding them together. Okay, and that's going to be the top line of whatever this equation is. Okay, so what? Grab the wrong thing there. Okay, so what is this then? What are we looking at here, which is the main part of the equation? What we're saying there is we're going to have any number of observations x. Remember we said whatever data points we have, we're going to call them observations, and we could have 2, 3, 4, we could have 10,000, 50,000 observations, whatever it is that we have. Remember, we didn't talk about it yet, but we're going to talk about something like IQ scores. There's millions and millions of IQ test scores that have been taken over the years. So this number could, this number of observations could really be anything. Here's the average cleaning hours at the Stayside Hotel. And, you know, there's quite a few observations there. There might be 20 or 25 observations there. That's what this X represents, all of these individual observations. So we're going to take each and every observation, 16, 13, 12, 14, 10, 12, 14, 10, 15, 17, each one of those, and we're going to subtract it from the mean of those observations. In this case, it just happens to be 13.13. And then we're going to square that. And the reason we square that is because if we didn't square it, when we string all these observations together, it would just equal 0. So we need to square it to make it positive, and then we'll have a number that we could deal with, that we could interpret. So the very first thing we'll start with is, let's use this as an example. 16 minus the average. This is mu. We might have talked about that before. This is mu, and this means the population average is 13.13. Okay, and then what I would do is I would do that calculation first, 16 minus 13.13, and then I would, I don't know if I could do it here. No, I'm not going to be able to do it here. I was going to put a postscript up there. So I would square that. Okay, so 16, which is the first observation, minus the population average, which is 13.13, do that calculation. Then I would square it, okay, and that would be my first value on this numerator here, the top of the equation. Then, again, according to this sigma, I would add the next calculation in that series. So the next one would be 13 minus 13.13 squared plus 12 minus 13.13 squared plus 14 minus 13.13 squared. And I would go all the way along here until I finally got down to this last observation, this last x. It would be 15 minus 13.13 squared. And then I would go ahead and I would add all of those together to come up with my numerator. and then divide by the number in the population. This obviously isn't a population, it's a sample, but if it were a population, I would divide by the number in the population, right? Okay, so then I get that number, whatever it might be, and I have to remember to do this. Most students forget to do this. I need to then take the square root of that. The square root of that number. And most hand calculators have a square root function. And the reason I take the square root of it is to kind of get rid of all these squaring of things that I did. If I don't take the square root of this, I get something called a variance. And it's a very big number and it really doesn't mean anything. Once I take the square root of it, it becomes a standard deviation. And in later videos, I'm going to tell you how to interpret those standard deviations. And I'll give you an example of something you could do. I think it was IQ scores. That'll tell you really a lot of information based on that. So that's the calculation for standard deviation of a population. And then we have it for the standard deviation of a sample. And this is a much better example of a sample, right? We have 30 required for 30 housekeeper workers to each one clean a room. So how long does it take for them to clean a room? And we took a sample size of 30 here, and we got here's the number of hours that it takes the housekeepers to clean a room. So we know that's a sample because of the, if we were doing this calculation because of the S here. We still have our sigma, so this top part is kind of similar. The only difference really is we're going to be using the mean of the sample as opposed to the mean of the population, okay? This calculation, this formula here is one we will use far more times than this, because a lot of times we just don't have that population number. We have the sample. So we're using sample data when we're doing our calculation. So the same thing though would be the first observation minus the average of the sample squared plus the next observation minus the average or mean of the sample squared plus, and we go all the way down to the last one, 15 minus 13.13 squared. And then we divide that by n minus 1. So we take the number of observations here and we subtract 1 from it. And the reason, there's a number of reasons why we do that, but it has to do with error and the shape of the curve itself. So remember to do that too when you're dealing with a sample. Take the number of observations minus 1. We get a number, we take the square root of that, we have the sample standard deviation. Okay? And again, that's going to tell us a lot. It's going to tell us, once we get that number, we're really going to be able to look at the data and make a lot of inferences about what things mean. And ultimately what we're trying to do, and this is very important, ultimately what we're trying to do is find the proportion underneath the curve. We're trying to find an area or proportion underneath the curve. So let me just put a shape in here. Let's use this blue one for example. So ignore these other two curves. This blue curve, if I strike it right down the middle, right down the middle, we could assume, or it's true, that on this side is about 50% of the curve, or is exactly 50% of the curve, and this side is exactly 50% of the curve. That's going to tell us some information. That's useful to an extent. But I want to find the area under the curve in different places. What if I wanted to find the area of the curve under here? Because that's going to tell me what proportion or percentage of the data would fall out here, or maybe out here, or maybe out here, or maybe I want to find, maybe I want to find what proportion of the data or the population would be out here. And again, remember, that's what we're doing. When we're pulling a sample, we're trying to make inferences about the population, right? We can't take all of this data and information. It's too much money, too time consuming. So we're going to do a sample, and we're hoping that sample tells us about the population. And then based on that, the mean and the standard deviation, we can make some inferences about the population. And that's ultimately the goal of statistics, is to be able to take a sample, use good data, and make some inferences about the population. Okay, so let's go ahead and analyze this real quick using Excel, and we'll find the population standard deviation and the sample. No, actually, what we'll do is we'll do the sample standard deviation. We'll just do that one because I think we're going to be dealing mostly with samples. I'll show you where you find the formula though for the population standard deviation also. Okay, so here's the problem we're working with over here. The times required for 30 housekeeping workers to each clean one room at Stayside hotels are given below. So there's 30 workers, which means we have 30 observations, and the time, I don't know if that's in minutes or hours. I hope it's in minutes and not hours, but the time it takes for each housekeeper to clean one of the rooms. Let's say it's in minutes just to make it seem not so crazy. So 16 minutes, 13 minutes, 12 minutes, all the minutes. So it says here, use Excel functions to calculate mean, median, mode, range, sample variance, and sample standard deviation. We won't do all of that right now, but I'll show you how to figure out both a population and a sample standard deviation. I'll show you probably, again, I think I did this before, how to do some descriptive statistics and just get all of this information at once. And then we will show you, I had one more thing in mind there, but I can't think of it right now. Some small interpretations. I have two separate videos for interpretations. So don't get frustrated if you say, okay, great, there's a number. What does that number mean? The other videos will clarify that, help clarify that for you. So here's the numbers. I listed down just to make it a little easier. Here are the 30 housekeepers, and you know, is this a sample or is it a population? That's a little bit of a tricky question, right? Because this is how long it takes each of those 30 to clean the rooms. So you would say, okay, that's probably a population because it's telling me how long it takes each one to clean the room. Or we might have just taken a sample of each one time and done that. So you wouldn't be wrong necessarily in saying, oh, it's population, I did this calculation, or it's a sample, I did this calculation. This deviations are not going to be that far off either way. So let's go to formulas, okay, more functions, statistical. And then if we go all the way down to standard deviation, here's a standard deviation for a sample and a standard deviation for a population. You see it kind of says it right there when you hover over it. So stdev.p, stdev.s, population and sample. Let's do a sample first. Let's assume it's a sample. And the first set of numbers is just going to be this here. I'm not going to include the average in there. If you do calculate the average, make sure you don't include it in the actual numbers themselves. So if you look real quick, you can see right here, 2.873 is the sample standard deviation. Is a sample standard deviation. And just to give you a real quick, again, there's videos dedicated to this, just give you a real quick idea of what information this holds. If I take this number now and I subtract it from the mean and I add it to the mean. So I'm going to take over here and I'm going to subtract that number from the mean. I'm going to take this number and subtract it from this number. So go this minus this equals 10.26. And what I'm going to do on this other side here is I'm going to add that number to the mean. So this plus this equals this. So now we have two numbers spread a little bit, okay? And we have 10.26 minutes and 16.01 minutes. Okay, based on the normal distribution curve and the empirical rule, I know that 68% of all of these observations, almost 70% of them fall between 10.26 minutes and 16.01 minutes. So almost 70% of the ladies or men who are cleaning the rooms, 70% of them could do it between this time and this time. Okay, so if I have somebody doing it out here, 2 standard deviations, or out here, 3 standard deviations, that's a long time. And if I have somebody doing it way down here, maybe this 8 minutes or less, that's doing it in a really good amount of time, right? There's very few that could do it there. Most, 70%, are going to be doing it between 10 minutes roughly and 16 minutes. Okay, and that's an area under the curve that would be somewhere here, and then draw another line on the other side, and that area under the curve, that close to 70%, will be between 10.26 minutes and 16.01 minutes. Okay, so if we, instead of just getting the single standard deviation calculation number 2, we could do what we did in another. We can go to data and data analysis and do our descriptive statistics. And if we specify, I'm going to bring this over here so we could, if we specify a range, or if we specify our variables, and then I'm going to put it right here, and then summary statistics, make sure that's checked. Okay. This is our summary statistics here. It gives us our mean, which we knew. It gives us our median, our mode, our standard deviation, which we said was 2.87. The range of numbers, the sum, the count is 30. We know that. So just from this, we can get our mean and our standard deviation and get some of this other information that we might find useful instead of just getting the number itself. Okay, so that's our lecture on what is a standard deviation. I know it was a little long, and I apologize, but it is such an important concept. We figured out how to get a standard deviation. We talked a little bit about its interpretation. In the next video, we're really going to talk about what's called the empirical rule and figure out when we have 1, 2, or 3 standard deviations away from the mean, what all of that means. And just to give you a little spoiler alert, 3 standard deviations below, 3 standard deviations above. If we add those together, 3 and 3 is 6. It's where we get 6 sigma. Okay, so when we're talking about sigma, we're talking about this standard deviation and why it's so important and why the interpretation of it is so very important.